I was looking back at the notes from the previous video and it looked like quite a mess. And it's a complicated thing to talk about. We had a lot to write down. But let me make sure you understand the take-home message from that previous video. When we look at a reaction, it's important for us to predict whether it likes to go in the forward or the backward direction or neither. And the way we do that is by looking at the delta G naught prime. And for this reaction, the splitting of ATP to ADP in phosphate, we said the delta G naught prime was negative 30. Negative means it is going to have a propensity to go in the forward direction, and 30 means it's a pretty large propensity to do so. When we looked at the other reaction below, putting a phosphate onto glucose to make glucose 6-phosphate, we said that it has an uphill delta G naught prime of plus 14 kilojoules per mole. That means its propensity is going to be in the backwards direction toward the substrates. So that's how you do it. You look at the delta G naught prime, particularly the sign. But that raises the question, where does the delta G naught prime come from and how do you know it? How do you estimate it? Well, that's our next topic, and we're going to skip over what's at the bottom of the page here and come back to it. And we're going to go on to the next page and talk about high energy linkages. And what we sometimes refer to these as is currencies. We've already used the idea that ATP is a currency for the cell, and we've just demonstrated that it's got quite a bit of free energy to give when it breaks its phosphate off. Now remember, on the previous page, let's go to the middle here and note that on the previous page we said it was a phosphoanhydride, or a PA, that we're breaking when we do a ATP split into ADP and phosphate. So it's the phosphoanhydride that is got some energy, potential energy in it, and that we can then use if we break it. So if we break any phosphoanhydride, it's delta G naught prime. Let's make a column over here, delta G naught prime. And I'm going to put an approximate there because every phosphoanhydride is different, but they all are going to have roughly 30 kilojoules per mole, and it's going to be negative when we split it. Now, when we think about currencies, I like to think of ATP and the phosphoanhydride that it contains as kind of like the $20 bill. I mean, think of when you go to the ATM and get out $100. You don't get ones or fives. That's unwieldy. And they don't give you hundreds either, because that's also difficult to break if you go out to a small store. The $20 bill is a nice intermediate value. It's got enough value to purchase a lot, but it's not unwieldy. Same with the anhydride. It turns out it's not the highest or the lowest energy that we have, and that makes it extremely useful. Let's take a look at some other ones that we might be interested in. Down at the bottom is the phosphoester. And if we break the phosphoester with water, we end up with an alcohol and a phosphate. Now remember, a phosphoester is a carbon-oxygen P double bond O. And when we break it, we end up with the alcohol and phosphate, like I just said. Now if we break that, it is favorable to do so, but less so than an anhydride. It's got about negative 15 kilojoules per mole. So maybe we could think about this more like a $10 bill instead of a $20 bill. It's still got value, but it's not as much as we saw above. Okay, let's keep doing these. Right up here, we have something slightly different than what we saw before. Here we have a C double bond O, bridge O, P double bond O. That's actually a carboxylic acid, or carboxylate, and a phosphoric acid coming together, and we have a special name for that. We call that an acyl phosphate. After all, when we took fatty acids that were carboxylic acids and attached them to glycerol, we called that an acyl glycerol. Well, any carboxylic acid that we attach to something else can be called an acyl group, and this acyl phosphate can be split into a carboxylate and a phosphate with a water, and we get approximately negative 50 kilojoules per mole. So, in terms of currency, maybe we could think of that more like a $50 bill. Much more value than the anhydride. But notice they're all negative. They're all favorable when we use water to break them apart. Let's keep going. Up here, we have a unique situation in which we have a linkage here of a phosphate. And when we break it off, we end up with an alcohol right here and a phosphate, which we need to draw in there. We'll just call it a PI, like we said on the previous page. Inorganic phosphate can sometimes be just listed as P subscript I. Now, when we break this and end up with an alcohol, you would think it is a phosphoester, like all the way at the bottom of the page. And in fact, it is a phosphoester. But it's a very special phosphoester, and it's going to raise the value of energy in this linkage tremendously. We're going to see that this is actually negative 60 kilojoules per mole, approximately. And the reason for that is because when we break off the linkage, the phosphate, and create an alcohol, like I said before, it's a phosphoester. So we get about negative 15 kilojoules per mole, just like we said at the bottom of the page. But when we create this special alcohol, let's take a look. It's an alcohol right next to a double bond. That's a very rare situation. We call that an ene for double bond, ol for alcohol. And the molecule on the left is therefore an enol phosphate. And maybe you remember from organic chemistry, I suspect they taught you this, that enols are very unstable, and they're going to automatically transform themselves through what we call a tautomerization into a ketone. And that's so incredibly favorable. It's about maybe negative 45 kilojoules per mole. You put these two together and you get basically like you're falling off a cliff here. It's negative 60 kilojoules per mole. So this enol phosphate is our most valuable currency that we have in our wallet full of cell currencies. There's one more to talk about, and we'll see it down here in the intermediate area. That's going to be a new type of a linkage. It's also negative 30 kilojoules per mole. So we could say it's another $20 bill, so to speak, because it's equivalent to an anhydride. And what we have is a thiol linked to a carboxylic acid, and we make something that kind of looks like an ester. It's going to be a CS C double bond O. Instead of a CO C double bond O, it's a CS C double bond O. We call this a thioester because it's like an ester with a thiol sulfur in it. And we're going to use this for 5 weeks constantly. It's an important linkage, and I want you to recognize it. So these two linkages are very different, the anhydride and the thioester, but they're equivalent in energy. It's maybe like thinking about an American $20 bill and a Canadian $20 bill. They have different color, they look different, but they have about the same value. So we're going to use these currencies, and what's important for you to do is to know them. You're going to want to recognize the presence of these linkages and understand what the energies are. You have to memorize these, what the energies are when you break them. And then we have to recognize that we can flip this page left to right, and we can go backwards. For instance, we can take a phosphate and an alcohol, take away a water, and generate a phosphoester. And in that case, we end up with the reverse delta G naught prime of, remember, plus 15 kilojoules per mole to go backwards. So we're going to be using these 10 linkage breaking and making throughout right on to the final exam. 5 in the forward direction, breaking, that are always negative. 5 in the reverse direction, making bonds, always positive and uphill. I'm going to practice this a lot in the homework.